Hi viewers. Welcome to this presentation on active power matching mechanism in power system. The statement that power system frequency depends on load generation balance and this power balance is known to power engineers. Let us review analogy to understand in details how power and frequency reacts. Following water supply regulating system will be useful to understand the process. This is sketch for water supply system. Regulating tank T has 400 kL capacity. Water to tank T is received from upstream infinite capacity reservoir R. Inflow piping runs from bottom of reservoir R up to bottom of the regulating tank T. Valve VG in the line is to adjust inflow as required. Outflow piping is from bottom of tank T. Valve VD in the line is to adjust outflow as required. Initially tank has 200 kL water. Inflow and outflow are adjusted to 20 kL per minutes by valves VG and VD. Water in the tank T is steady at 50% level. Now outflow is increased from 20 kL to 25 kL by valve VD. So 5 kL water shortage occurs every minutes. Consequently water level in the tank starts dropping. Here can we estimate when tank will be empty. Obvious answer seems to be after 200 divided by 5 equals 40 minutes. Let us review general observation before any comments on the answer. This is backyard water tank used for routine household work. Water flow is adjusted as required by opening of the cock. Cock is opened fully for maximum water flow. But sometimes water flow is meager even after full opening of the cock. Why it is so? Any layman concludes that water in the tank is very less and requires refilling. Laymen don't know the science about this fact, but engineers know that water flow depends on pressure at outlet in addition to opening of outlet. Pressure in this case is water head above the outlet. Again back to review the case of regulating tank with the conclusion that water flow depends on opening at outlet and water head above the outlet. Water head Hg is between water level in tank and reservoir. Water head Hd is between outlet at bottom and water level in the tank. Water level in tank was dropping due to increased outflow. Now dropping of water level is increasing the head Hg. Consequently inflow is automatically increasing from 20 kL without any adjustment of Vg. Same way dropping of water level is decreasing head Hd. Consequently outflow is automatically decreasing from 25 kL without any adjustment of valve Vd. This phenomenon of dropping level, increasing head Hg, increasing inflow, decreasing head Hd and decreasing outflow continue till both inflow and outflow are equal. Ultimately water level in the tank will be steady again at level lower than previous. Thereafter no further drop of level and hence tank will not be empty. Same thing would have happens if valve Vg was partially closed. Level dropping due to reduced inflow compared to outflow. Consequential automatic correction by increasing inflow and decreasing outflow till matching of inflow and outflow. But reverse happens when valve VD closed to reduce outflow or valve VG is opened to increase inflow. Water levels start rising due to excess water in the tank. Rising level causes decreasing head Hg and increasing head Hd. Consequently, inflow decreasing and outflow increasing. This continues till inflow and outflow matches. Levels stabilize at higher than previous. Comparison with power system. Tank T represents power system. Water level in tank represents frequency. Midway water level means 50 Hz. Water inflow to tank represents power injected in system. Water outflow from tank represents power drawn by users. Valve VG represents generation in service. Valve VD represents loads in service. Comparison of dropping level with power system. Water level in the tank was steady till inflow and outflow were equals. Unbalance occurs due to increase in outflow by opening valve VD. Inflow falls short of increased outflow. Level drops due to deficit of water in the tank. Level drop continues till inflow and outflow are equals. Frequency remains steady till load demand and generation are equals. Unbalance occurs due to rise in demand by addition of load. Generation falls short of increased load demand. Frequency drops due to deficit of power in the system. Frequency drop continues till generation and load demand are equals. Theoretical review of dropping frequency. We know that power plant is the device converting mechanical input power to electrical output power. Therefore, PM is equal to P plus PL. Where PM is mechanical power, P is electrical power and PL is power loss in the device. Difference PM, P is accelerating power Pa, ignoring small power loss PL. Load demand increased due to load addition. Increased power demand met by increased electrical power. Unbalanced power is accelerating power Pa is equal to PM P. Pa is negative because P PM. Pa is equal to moment of inertia times angular acceleration is equal to I times rate of change of angular velocity is equal to I times delta omega delta t. Rate of change of angular velocity is equal to Pa I. It is negative means system slow down and frequency drops. In short, additional mechanical input required for increased electrical output is drawn from kinetic energy of rotating power plant. Consequently, rotating system starts slowing down. Governor system as closed-loop control increase mechanical input power to prime mover and arrest dropping speed and frequency. Comparison of automatic inflow rise with power system. Head Hg increasing with dropping level. Inflow increasing with increasing head. This process of dropping level, increasing head and increasing inflow continues till inflow is equal to outflow. Frequency drop is sensed by governor. Governor acts to increase input mechanical power to prime mover. The process of dropping frequency and increasing prime mover power continues till mechanical input power equals electrical output power, PM is equal to P. Power frequency chart for governor control. Power system was operating at point O with demand do, generation go and frequency fo. Demand increased from do to Dn. Frequency drops from fo to Fn and generation raised from go to Gn by governor. Load demand characteristic. Power required by electrical motors depends on device coupled to it. 1. Power drawn by motor depends on load factor. User dependent. 10 HP motor may draw 5 to 15 amps depending on loading on flour mill coupled to it. 2. Power drawn by motor depends on speed of load. Supply dependent. Power drawn by ceiling fan depends on speed of the fan. Speed of motor depends on supply frequency. Ultimately, power demand of motor changes with frequency. Such loads are frequency-sensitive or frequency-dependent loads. Sensitivity of different types of load with respect to frequency is different according to type of devices. Power drawn PO is equal to PN for Fn x, where PO is power drawn at operating frequency. Pn is power drawn at normal frequency. Fn is normal frequency. Φ is operating frequency. X is index according to type of load devices. Heater is resistive load. Power drawn is V2R. It is independent of frequency. So X is equal to 0 for similar loads. Flour mill is constant torque load. Power is equal to torque times angular velocity. Angular velocity proportional to RPM is proportional to frequency. Ultimately, power is proportional to frequency. So X is equal to 1 for similar loads. Similarly, X is equal to 2 for compressors and similar loads. Similarly, X is equal to 3 for pumps and similar loads. And so on. Power system consists of various types of loads. Proportion of these loads is ever changing. Therefore, average change of power demand due to frequency variation is unpredictable. However, approximate change in power demand with variation in frequency is around 3 to 4% per hertz change in frequency depending on load mix of particular system. Comparison of decreasing outflow with power system. Water level dropping due to shortage of water in the tank. Water head HD reducing due to dropping water level. Outflow decreasing because of reducing water head. Process of dropping water level, reducing head and decreasing outflow continue till outflow is equals to inflow. Water level stabilize at this new level. Frequency is dropping due to power demand higher than generation. Dropping frequency influence sensitive loads. Power demand decreasing with dropping frequency. Process of dropping frequency and decreasing power demand continue till power demand equal power generated, PD is equal to PG. Frequency is stable at this lower level. System frequency is dropping due to shortage of power when load is added in the system. So on one side governor system increasing mechanical input to prime mover. On other side power demand is decreasing with dropping frequency due to load bias. Ultimately frequency drop is arrested when increased generation and reduced demand matches at lower frequency. Similar phenomenon occurs during loss of generation. Dropping frequency, increasing generation, decreasing demand and stabilized at lower frequency when generation and demand matches. But reverse occurs during adding of generation or loss of load. Frequency is increasing due to excess generation. Hence generation dropping, demand rising and stabilizing at higher frequency when generation and load matches. Therefore, ideal power frequency chart may be like this. Load demand changes with frequency because of frequency-dependent loads. System was operating at O with generation go, demand do and frequency fo. Demand increased from do to dx. Frequency dropped from fo to fn because of power shortage as dx do. Generation increase from go to gn, demand decrease from dx to dn. Operating point shift from O to N where demand Dn is equal to generation Gn at frequency Fn. Frequency drop is less due to frequency-sensitive load. Otherwise, frequency could have dropped to Fm. Governor was essential part for stability power plants. Governor has important role for adjusting input power as per load variation in case of standalone and group of generators. But power system expanded with different types of power plants at different locations. Then power plants were operated as base load stations and regulating stations depending on feasibility and generation cost. Base load stations operated at maximum without consideration of frequency. Role of governor is limited in grid mode operation of power plants. Grid has many agencies for generation, transmission and distributions. All have own operating strategy regarding generation, distribution and exchange with others according to own feasibility, constraint, economics, etc. Hence, grid operation at steady frequency is not feasible. Variation in generation and/or load in any constituent changes common grid frequency. This reflects on all power plants on active governor mode. Variation in generation disturbs merit order schedule. Frequent variation of generation is not feasible nor healthy for most of power plants. Consequently, situation may arise for any constituent when cheap generation is reduced due to frequency rise and import costly grid power. Similarly, opposite situation may also there when costly power increased due to frequency drop while foregoing cheap grid power. Automatic generation variation may pose problem of critical loading in some section in transmission network. Therefore, governor passive mode operation is preferred for most of the generators in grid system. Corresponding water supply set up with short inflow line above water level instead of submerged. Practical load frequency chart. Generation without droop, passive governor. Demand changing with frequency, sensitive lower. System operating at O with generation go and demand do at frequency fo. Load increased from do to dx. Frequency drops to Fn. Demand drops from dx to do is equal to dn is equal to go. Operating point move to n. Governor is not to maintain constant frequency, but arrests deviating frequency within limit according droop and load gain. Frequency-sensitive load has key role for frequency control. Frequency is steady when generation and load demand is balanced, but not always normal frequency. Automatic matching of generation and load demand by governor and load bias is limited to small mismatch. Complementary corrective system adjusting generation and/or load demand is required while large mismatch to save the power system. Frequency deviation, unhealthy condition of power system is due to mismatch of generation and load demand, but the frequency deviation itself eliminates, cures the mismatch. It is like Ghalib's saying, दर्द का हद से गुजरना है दवा हो जाना. means peak pain becomes medicine. Request. Please like, subscribe and recommend others if found worthy. Viewers' comments welcome. Thank you viewers. Bye until meet again in next episode.